Hey everybody, welcome to AP Calculus AB. We are starting Unit 2 today, which is on differentiation, and this chapter is about the definition and basic derivative rules. Today's focus is topic 2.1, which is defining average and instantaneous rates of change at a point. Enjoy! All right, everybody, welcome to Chapter 2. We've got Chapter 2 starting off. Chapter 2 is on differentiation and fundamental properties of differentiation. Today's focus is at 2.1, average and instantaneous rates of change. So you might remember back in Chapter 1, at the very beginning of Chapter 1, we talked about these a little bit, but we're going to get more into them today. We'll review them a little bit, and then we'll lead into some things that we're going to need for Chapter 2, specifically about this thing called the derivative, which is a huge topic in Chapter 2 and in calculus in general. Again, this is AP Calculus AB. We will be using calculators for this lesson. They are necessary for this lesson. So if you've got your TID3 or TID4, that's going to be really helpful for you to have out. Remember that I've also posted links to the Chromebook version of the calculator that you can be using as well if you don't have your graphing calculator at home. If you happen to have other graphing calculators, you're welcome to use those, but you may need to look up the steps. The steps that I'm going to be going through today and in lessons going forward are going to all just be for TID3s and TID4s, since that's what the majority of our students use. Two reminders for AP Calculus: when we do use calculators, always put your calculator in radian mode. That is really important when we're using sine, cosine, and tangent. And also, if you are rounding ever in AP Calculus, round to 3 digits after the decimal place. That is the standard. You can literally lose points on the AP exam if you round to 2 or 1. So please make sure that you're doing at least 3 digits after the decimal place. Let's get into today's lesson. So today's lesson, we're going to first recall rate of change. So we want to think back to Chapter 1 and think back to Algebra 1 about what a rate of change is. Rate of change is just a fancy word for slope. That is a fancy phrase for slope, is rate of change. And so going even back down to Algebra 1, we thought about slope as y2 minus y1 divided by x2 minus x1 if we were given two coordinates, right? Generally, the coordinates that we're talking about would be like x1 comma y1 and x2 comma y2. But we also know that a different way that we could represent this is sometimes referred to as the change in y divided by the change in x. This little symbol here is a little triangle, which in Greek letters is a delta. It's a delta. And all that means is the change. So it is the change in something in this context. But that's a Greek letter delta. Great, so we have the change in y divided by the change in x. And even if we think back to like even science classes, we might refer to this even as the change in the dependent variable. So we have a dependent variable, like per or divided by an independent variable. Normally the y value is your dependent variable. Normally your x is your independent variable. But all of these should be familiar in some ways if we're thinking about slope for this. Now, we also remember from earlier in this earlier in Chapter 1 that if we're talking about the average rate of change on an interval from a to b, that it's essentially the slope formula. It's essentially the slope formula, except instead of using coordinates like x1 comma y1 and x2 comma y2, we're going to refer to two coordinates, so one being a as the x value, and we're plugging it into a function, so our output would be f of a, and then the other coordinate would be an x value of b, which we then plug into the function and have an output of f of b. So if we were to find the slope between the two of those, the way that we would represent this is going to be f of b minus f of a, all divided by b minus a. This is our formula for the average rate of change. Normally we write it with functions and function notation in AP Calculus. And so this is what we'll see most frequently when we're doing average rates of change, is this formula. Highlight it, it's a big one to know. So first question here is for us to find the average rate of change from a function. they're telling us that that function is this f of x is equal to the natural log of 3x. This doesn't explicitly say it, but because of the way that this is written, it is sort of assumed that that 3x is inside of the natural log. Right? The natural log by itself is not a value, and so the 3x, just based on how it's written, and since there are no parentheses given, the 3x is assumed to be inside of that natural log, and they're asking us to do it over the interval from 1 to 4. So what does that mean? Well, if we're thinking about our average rate of change equation that we've got right here, what we're going to do is we're going to plug in 4, we're going to plug in 1, and then we're going to be dividing. So what we would expect to see for this, for that average rate of change, just see ROC, average rate of change, it's going to be whatever f of 4 is minus f of 1 divided by 4 minus 1. And we can see from that function, if we plug in, that this is going to be the natural log of 3 times 4 minus the natural log of 3 times 1, all divided by 4 minus 1. Now we're going to get into the calculator part. So we know that we can plug essentially this entire expression into our calculator. I'm going to show you now how we might do that. There are going to be sort of two ways to do it. So let's talk about it. Okay, so our first way, since this function is the natural log of 3x, and that's a pretty short function, would be just to type in the expression. So we've got in the numerator, in parentheses, the natural log of 3 times 4, which would be 12, minus the natural log of 3. Again, we put the numerator in parentheses, and we also make sure we put the denominator in parentheses, so 4 minus 1. If we were more complicated than that, we could just say 3, but that's going to give us an answer which is about 0.462. Again, we always round to 3 digits after the decimal place, and so that's where we would stop for our answer here. Now I'm going to give a second way to do this, which is particularly useful if it's a more complicated function. We would go to our y equals, and we would type the function in. So in this case, this is the natural log of 3 times x. So a natural log of 3 times x. And we're going to second quit back to our home screen. Next, I'm going to go to my variables. Actually, so I'm going to put parentheses. I'm going to go to my variables, and I'm going to go to yvars, my y variables, and hit function, that first one. And we're going to have it call the equation that's in y1. So we're going to hit y1. And we can do this essentially like function notation. First, I want to plug in 4 for that function. Then we're going to subtract, and then I'm going to go again to my variables button, go up to yvars, hit function, y1, and then we're going to now have it plug in the second input, which is 1, closing the parentheses for that numerator, and then dividing by 4 minus 1. That's going to give us the same value, which is 0.462. Now again, the second method of using essentially function notation on the calculator is really useful in problems that have like multiple inputs, where you don't really want to retype the whole equation over and over again. This is nice because you just type the equation in once, and then you're using the function notation in order to actually evaluate it. All right, so using the calculator, we saw that the solution to this problem for the average rate of change was about 0.462, so about 0.462. Again, we round our answer to 3 digits after the decimal place. Great, let's move on to the next one. If we're talking about average rates of change from a table, if we want to find the average rate of a change over the interval from 2 to 30, first off, be careful. Very frequently on the AP exam, they will give you a table that has actually more information in it than you need. So in this case, we're only talking about the x values between 2 and 30, so I'm only looking really at these values over here. I'm not worried at all about this over here. So if we're going to do that, again, our average rate of change formula is going to be f of 30 minus f of 2, all divided by 30 minus 2. And so plugging in from our table, we can see that f of 30 is 7, f of 2 is negative 2, and then we've got that 30 minus 2 in the denominator. So this looks like this is going to be 9 over 28 as our answer for this particular problem. So 9 over 28 would be our average rate of change between 2 and 30. All right, so this leads us into what the average rate of change is. So the following quotients express the average rate of change of a function over an interval. F of a plus h minus f of a divided by a plus h minus a, or f of x minus f of a over x minus a. So what is this? We had said earlier that essentially the way that we talk about the average rate of change is like f of b minus f of a all over b minus a. And so we can sort of see immediately that this is in that same form, right? They just switched the x value with the b, and it's the exact same thing. So then the question then is, what is this? What are these h's and what's that? What we have in this case is we're imagining sort of 2 points. One where we have the value a comma, if we plug into that function, the output would be f of a. And then the second point would be some h units away from the a value. And if we plug that in for f as the input, we would have f of a plus h. We might notice here then, just sort of comparing the two pieces, if we take do the average rate of change for this formula, we would have this minus, let's see, trying to do the different color, this f of a, so that's this right here. And then similarly, we've got this a plus h, which is that down here. And we've got our a, which is going to be right here. So what we're seeing is here, this is essentially our slope. It's like doing y2 minus y1 over x2 minus x1. And so that's sort of a nice way to write that with these h values. What I'm going to do is I'm going to show a visual of what this is. But before we get to that, I want to talk about this part right here. So they're saying that this is also the slope. It's also the slope of the secant line. So we might remember from back in chapter 1, we talked about if we have a curve, a line that crosses at 2 places is what we refer to as a secant line. That is a secant line. And so the average rate of change, again, is the slope of the secant line. That's a useful thing to know. But let's get into that visual, and we'll do that, and we'll come back. All right, so we've got a visual here from GeoGebra, the website GeoGebra, and we're looking at the function x squared minus 4x plus 1, right? That's this black parabola that we've got right here. And what I've identified here are 2 points. The first being some x value and its output, f of x. So if we plugged x into this function, the output would be f of x. And over here, we have an x plus h. So we have the x value that we had here plus some h extra distance, comma, f of x plus h. So this is our input, and then our output is f of that input. So what do we see here? Well, we notice sort of the nice part of this is that we can actually move this function. So let's imagine our x value here was -1. So our x value is -1. Notice that the h that we have here is the horizontal distance between the 2 points that are being highlighted. So if I move this point over here, say to like x equals 3, we can see that our h value is actually 1, 2, 3, 4. And that makes sense because if we take -1 and we add 4 to it, we would have 3, which would be this point. The nice thing about keeping these in this particular way, as opposed to showing the actual values, is that for these definitions of average rate of change and instantaneous rate of change, we can use them for any points. So it doesn't matter whether they're like decimals, if they're in between x values, or if they're actually on specific x values. But what is this finding? Our expression, which we said for the average rate of change, was at f of a plus h minus f of a all over a plus h minus a. Here we're using an x instead of an a, but same idea. What is this calculating? This is calculating the average rate of change, which is the slope of that secant line. So my secant line is this red line that we've got right here. And as we move these points along, what this is doing is it's calculating the slope of that secant line. So we see that it has a slope of like -1.333. If I go up here so that they're the exact same height, we see that that line is about horizontal, and we see that the slope is 0, which makes sense for that. If we lower this point to go to right here, we can see that our graph is going what? Up 1, 2, 3, 4, 5, and it's going right 1, 2, 3, 4, 5. So the slope should be 5 over 5, which is about 1. All this is doing, this expression, is it's representing the average rate of change between two arbitrary points on our graph. And so that f of a plus h minus f of a over a plus h minus a is going to give us that slope of the secant line for those points. Again, the h is simply the horizontal distance between your 2 points that you've got there. All right, so we just saw the visual of our average rate of change, right? And we saw the idea that we've got these 2 points, f of a, or rather a, an x value of a and an x value of a plus h, and that this is representing the slope between them. That average rate of change is the slope of that secant line. And this can be written either one of these two ways. This one we'll talk a little bit more about in the future. But let's talk about now instantaneous rate of change. So the instantaneous rate of change, which again is different from our average rate of change, the following limits express the instantaneous rate of change of a function at x equals a. And this looks pretty familiar from comparing the two of these. It's f of, the limit as h approaches 0 of f of a plus h minus f of a all divided by h, or the limit as x approaches a of f of x minus f of a over x minus a. These, if I take a look at these, are pretty much the exact same thing, except they're throwing this limit statement on here as x approaches a. And these are almost pretty similar. The numerator is the same. But in the denominator, we have just an h. Why do we only have an h? Well, if we take a look at this, right, this up here, if we were to simplify that, if we had that a plus h and we subtracted the a, those a's would actually cancel each other out and you'd be left with just the h. And so that's why that is in the denominator there, that h value. Essentially, it was the a plus h minus a that was here, but we simplified it to become an h. So we also notice that this has a limit statement on it. But what is an instantaneous rate of change? If we think back to chapter 1, we had said that this is the slope, so this is also the slope of a tangent line at some value x equals a. So it's the slope of a tangent line at x equals a. So if I were to have some sort of arbitrary graph that looks like this, if this were to be my a value, if that's my a, my tangent line would be the line that just barely touches. It has the exact same slope at that point. It would be the slope of the tangent line at that value. So the red line, the slope of that line, would be my instantaneous rate of change, which I'll say IROC. Let's switch back to our visual to talk about this limit. Why are these limits here? What's the limit as h approaches 0 for? And what is that taking into account? And how does that help us with the slope of the tangent line? Here we have a slightly different function. We've got negative 0.5x squared plus 6. We've got this parabola that's opening downwards, and similar to our visual from before, we have 2 points highlighted. One at some x value, where the output of the function is the y value, and then an h units over, we have a second point which is at x plus h, and then the output is going to be f of x plus h. And we can see maybe estimating some actual points here. Again, earlier we saw like sort of our average rate of change if we were trying to find particular values. Maybe in this case we see that it's going down 1 over 1. And so that average rate of change is this negative 1. But here we're talking about instantaneous rate of change, which we know is the slope of a tangent line. And the part that got added to this instantaneous rate of change is the limit as h approaches 0, as this h approaches 0. And again, h is this horizontal distance between these two points. So if h is approaching 0, that means that these 2 points are getting really, really, really close to one another. In fact, even closer than this h is getting closer and closer and closer to 0. And notice that as this point gets closer and closer to h is 0, that this secant line that we have is getting closer and closer and closer to being a tangent line, right? As if these were at about the same point, we would actually have a tangent line there, which we can sort of estimate here. So If h is larger, we have a secant, right, where it's estimating this average rate of change. But as h approaches 0, it actually gives us a really good estimate of the slope of the tangent line, which would be our instantaneous rate of change. And so we can sort of see that tangent line, that's matching up there really nicely. And again, the nice thing about keeping these as x and f of x and x plus h comma f of x plus h is we can move these points anywhere we want. So let's say that this is where our point is at x is equal to 1. Again, as the h value gets closer and closer and closer to 0, that means this point is getting closer and closer and closer to the other point. And we see that that red secant line gets closer and closer and closer to that green tangent line that we've got right there. It gives us a great estimate. And the closer that we get to it, the closer of an estimate that's going to be to the real instantaneous rate of change, which would be the slope of the tangent line. All right, so now that we've seen that, let's get on to our next piece. We're saying find the instantaneous rate of change of f of x is equal to x minus x squared at a value of x equals -1. We've got two different ways that we're going to approach doing this. I'm going to go through both of them, but we're using limits. We're using these limit definitions of instantaneous rate of change that we had from right here. And so we're essentially trying to find the slope of the tangent line of this function at x equals -1. That would be our instantaneous rate of change. Now, luckily for us, we just did a whole chapter on limits, and so we're going to be using that limit knowledge here in these two problems. Let's do it. So the question first is, we're saying a plus h minus f of a in that numerator. In this particular problem, we're going to essentially treat the x value that they gave us, this x equals -1, as the a value. So I'm going to say that actually a equals -1 for this particular like x equals a value. And so if we plug into that equation, we're going to see here that the limit as h approaches 0 of f of -1 plus h minus f of -1 all divided by h. Next, what we need to do is we need to think about what the function f is, right? We're plugging -1 plus h in for our f, which means it's going to need to go into both of these x values. And then over here, when we do f of -1, we're going to plug in -1 for both of those values. So what does that equal? Well, it's the limit as h approaches 0. We need to write that limit statement all the way through until we take the limit. And again, I'm plugging -1 plus h in for both of these x's. So this is going to be -1 plus h minus -1 plus h quantity squared. So right now, what we've done is we've done this part, and now we've got minus f of -1, so that is going to be -1 minus -1 squared. That is going to be the second part of this, so we'll do that here. And then we're dividing this all by h, so this is all being divided by h. Well, this looks pretty messy, but luckily for us, we're going to be able to simplify some things. So let's do some algebra here. So we've got this -1 plus h, -1 plus h. And what I'm going to do here is I'm going to expand, right? -1 plus h quantity squared. We can do an expansion box for that. And if we do that, that's going to be, what? H squared minus 2h plus 1. Then we've got over here on this part, I've got a -1 minus -1 squared. -1 squared is 1. -1 minus 1 is going to be -2. So that is a -2 in those parentheses, and then we've got our h value here. Okay, next I need to make sure that I remember to distribute this negative sign to each of those things inside there. And if we do that, we're going to have, again, the limit as h approaches 0 of what? -1 plus h minus h squared plus 2h minus 1, and then plus 2 because we've got a minus and a minus there next to each other. And then that's all being divided by h. Well, luckily for us, it looks like some things are going to cancel out here. If I were to take -1 and -1 and then I add 2 to it, those are going to go away. So I'm able to simplify some things right off the bat, which is nice. This is the limit as h approaches 0 of what's left. Well, I've got an h and another 2h, so h plus this 2h is going to give us 3h. And then I've got that minus h squared that's right here. So the h plus the 2h gave us 3h, and then we've got a minus h squared. That's all being divided by h. And what we can then do is we can factor an h out of that numerator and cancel. So the limit as h approaches 0 of h times 3 minus h, all divided by h. We get those h's canceling each other out. And then I get that this is going to be the limit as h approaches 0 of 3 minus h. Now there's nothing left to actually solve or simplify. We're just going to do direct substitution. If we plug in 0 for h, our answer for this is going to be 3. So what did we just find? We just did all this limit work. And it looks like quite a bit to find this instantaneous rate of change, and it was. It was a lot of steps. But this is essentially our formal definition of what an instantaneous rate of change is. And again, what is this? This is going to be the slope of the tangent line at x equals -1 on the function x minus x squared. So the slope of the tangent line at x equals -1, from doing this work, I can tell you it's exactly 3, which is sort of nice considering, I haven't even graphed it, I haven't even really looked at it. That's pretty cool. All right, so that is one of these. We also want to see this other form. The only good news that I'll tell you, all right, we're going to be doing this limit stuff for the first couple of lessons in this chapter, but there is a shortcut for finding this instantaneous rate of change, aka the derivative, which we're going to be getting into what a derivative is. That doesn't require us to use limits, and that's going to be really nice, but sort of an understanding of what this instantaneous rate of change is and how it relates to limits is really, really important as we get into this chapter. So we're going to spend this time doing it. We're going to focus on the second one here. So in this problem, we've got the limit as x approaches a of f of x minus f of a all divided by x minus a. Now again, same as in the previous problem, I'm essentially saying that my a is equal to -1. And if we look at the function was f of x is equal to x minus x squared. Okay, let's plug in what we know. So this is going to be equal to the limit as x approaches -1 of, well, f of x is just the function, right? They're not saying plug in anything here, just tell me what the function is. So that's going to be x minus x squared for our f of x. And then if we do f of a, we know again our a value is -1, so -1 is going to be put into that function. That's going to be -1 minus -1 quantity squared, and that's going to be divided by x minus -1 down there in that denominator. Well, how do we simplify this? Well, this is the limit as x approaches -1 of, what do we have? We have x minus x squared. Here we have a -1 minus -1 squared. -1 squared is 1, so -1 minus 1 is -2. And then I have a -2, so we're essentially adding 2 to this particular one. And then we are still dividing by x minus -1, so x plus 1 down in that denominator. Well, this one's a little bit different from the one that we had above. Here, this looks like, maybe we're going to be able to factor that numerator and hopefully have some things cancel out. In fact, I'm sure if I plugged in -1 in both of these, we would have indeterminate form. And so that sort of gives us an indication that we should try to factor and simplify. Well, how do we do that? Well, what I'm going to do first is, let's rewrite this. So this is the limit as x approaches -1. I want to actually factor a negative out here. And so this is going to be -1 times x squared minus x minus 2, all divided by x plus 1. And we're going to say that that is equal to the limit as x approaches -1 of -1 times, what does that factor to? Looks like that's going to be x minus 2 times x plus 1, divided by that x plus 1. Luckily for us, we see some factors that cancel each other out. And so we can see that this is going to become the limit as x approaches -1 of just -1 over -1 times x minus 2. We're into the direct substitution phase, so we plug in for that x as -1. This is going to be -1 times -1 minus 2. Negative 1 minus 2 is negative 3. Negative 3 times negative 1 is positive 3. Hey, that's the same answer as what we had up here. Notice. So essentially what we've seen is two different ways to find the instantaneous rate of change using our two different definitions. And so if I scroll back up to these, we again said that this instantaneous rate of change had two definitions. One was this, or we could use the second one. Notice one of them has the limit as h approaches 0, the other one has the limit as x approaches a, and we are finding the slope of the tangent line at x equals a. So it sort of makes sense that since, in this case, since our function was the same in both of these and was at the same value, that we would have the same slope of the tangent line, regardless of which of our limit rules that we use. And so that's good that we got the same value. I'm definitely positive. Great. So as we had said in this, we're going to learn lots of shortcuts in this on how to take these derivatives and how to do derivative rules. But instantaneous rate of change, doing this limits, it's useful for the first couple times, but it's not actually really tested all that much on the free response of the AP exam. If we're thinking about how this is actually tested, it's going to be tested in questions like this one, which frequently come up on like the multiple choice exam. And so what is it? Well, identify the function we're working with. Then identify the x value for the instantaneous rate of change, which is the slope of the tangent line at a point. So here's what our problem looks like. Number one, limit as h approaches 0 of 5 ln of 2 divided by 4 plus h minus 5 ln of 1/2, all divided by h. What is the original function? And then what's our instantaneous rate, or rather, this is asking us to find the instantaneous rate at what x value. Again, the two sort of like big equations that we've got for this particular chapter and for this particular section is this first rule, which says the limit as h approaches 0 of f of a plus h minus f of a all divided by h. Or the other one which we had was the limit as x approaches a of f of x minus f of a all divided by x minus a. These are the two possible rules it could be, especially if we're talking about instantaneous rate of change. These sometimes pop up in like hidden limit problems. You might be in a multiple choice section on the AP exam and you think you're looking at a limit problem, but it's actually a secret instantaneous rate of change problem. How could we tell? Well, one indicator here I see is that this is a limit as h approaches 0, which we know is of this form. And I'm seeing the denominator's got that h. These look really like they're similar forms. So the question then is what x values are we talking about? Or rather, what a values are we talking about? And what function are we talking about? I noticed that for the numerator, that it's got this 5 ln of 2 divided by 4 plus h. And then the f of a part is this 5 ln of 1/2. So if we're thinking about the numerator part, for the a plus h sort of looks very much like that 4 plus h bit. And so for me, I'm wondering if this is the equation, 5 ln of, so let's say 5 ln of 2 divided by something. So I'm going to say divided by our x. In this case, then, what do we have? This 4 plus h down here is the input for this function, and that would mean the a would be 4, and then we've got our plus h. So I'm thinking that this is an x equals 4. Would that make sense for this particular part then? If this is then f of a, which would be f of 4, well, if we do that, this 5 ln of 2 over 4, that's going to become 5 ln of 1/2, which is what we see. So that is sort of confirming for us that we picked the right values. This is going to be the function 5 ln of 2 divided by x when x is equal to 4. And so that's the setup for this. What about this one over here? Well, this one looks, I notice immediately this doesn't have the h's like this one does, but I do see it's like as x approaches pi over 2, and I'm seeing that sort of what looks like a difference quotient, like a y2 minus y1 over x2 minus x1 sort of form. So it's making me think that this is sort of the case. If this were to be the case, then I would think that the x value is going to approach our a value, which would mean that this is the instantaneous rate of change at pi over 2, right? That's from this piece right here, and that's also what we're subtracting there. Then what's our original function? Well, it's going to be whatever is right there, which is sine of x. Again, we want to check to make sure what we're saying is true. If this is the case, then that would mean 1 here would need to be f of a, aka sine of pi over 2. And if we think back to last week about our unit circle, even just sort of briefly sketching this, pi over 2 is going to be up here at 0, comma 1. So our sine is 1, and that's great for that. So I would say that fits for this. And that's going to be it for this particular lesson. Longer one just because it was the first one of our chapter 2, but we're getting into derivatives this chapter. As usual, we've got some practice problems for you to try. Check your answers as you go along, and then go on to your mastery check. Good luck. Have a good day.